What are microplastics? Microplastics are tiny plastic particles as small as 5 micrometer found in over 90% of bottled water. They pose health risks due to environmental harm, but detecting them is challenging due to their small size and low concentration. First, human consumption risk. Average person consumes a credit card's worth of plastic weekly through water and food. Smaller particles, smaller than 100 nanometer, may cross intestine barrier into the bloodstream. Chronic exposure linked to inflammation and oxidative stress. Second, regulatory gap. WHO acknowledge risk but cites insufficient data due to limits. We need to standardize the detection method in order to establish the safe threshold of consuming microplastic. The consumer also has right to know about the product safety. For scientific need, we need to understand the exposure levels and the particles characteristic. We also need to track the contamination through polymer fingerprinting. We also need to monitor the effectiveness of filtration technology. We are drinking plastic daily without knowing how much or what kind. Without accurate detection, we cannot assess risk, set safety standards, or hold companies accountable. This is not just science, it's public health protection. Our primary goal is to detect and identify multiple polymer types simultaneously. Next, achieve detection down to nanoparticle range smaller than 100 nanometer. Next is develop a rapid analysis time shorter than 5 minutes and a method that is suitable for quality control. And finally, validate against established methods such as FTIR and PYGCMS. For innovation focus, we aim to use novel SERS substrates for signal enhancement and implement machine learning for automated identification, and also design a protocol requiring minimal sample preparation. Why we choose SERS over other methods? Microplastic in bottled water are tiny. Some are over 1,000 times smaller than a human hair. They are also very hard to see, invisible to most methods. Other methods are either miss the smallest particles such as FTIR, destroy the sample such as PYGCMS, and take too long to analyze. The SERS is perfect for this due to it sees small invisible particles. It can detect particles down to 50 nanometers, which is incredibly small. It also works in water. Unlike FTIR, water does not interfere with SERS. It is also very fast. It takes about 2 to 5 minutes per test compared to others that takes hours or days. It is also very accurate. It gives a chemical fingerprint in order to identify the specific type of plastic. It is also non-destructive, which means the sample can be kept for more testing. SERS is also very portable, as it is some device can be handheld compared to other which is needed to be done in a lab.
Now, I move on to the spectral information reported in the literature using surface enhanced mass spectroscopy. The SRS spectra show clear and characteristic fingerprint prints for common microplastics such as PP, PET, and PS. For polyethylene terephthalate, strong bands are observed around 1,750 inverse centimeter, which correspond to C equals C stretching, and 1,730 inverse centimeters associated with C equals to oxygen stretching. In the case of polypropylene, characteristic peaks appear near 840 to 980 inverse centimeter due to carbon stretching, as well as around 1,450 inverse centimeter from CH inverse vibration. Polystyrene exhibit very distinctive features, especially the wing reading mode at approximately 1,000 inverse centimeter and aromatic C equals C setting in 1,600 inverse centimeters. These signals are dramatically enhanced when silver or gold nanoparticles are used as SERS substrates. These enhancements occur due to localized surface plasmon resonance, which generates strong electromagnetic field hotspot near the metal surface. Compared to conventional Raman spectroscopy, the signal intensity increased by approximately 10 to the power of 4 to 10 to the power of 6 times, allowing clear detection even for nanoparticles and plastics. As a result, the signal to noise ratio is greatly improved, enabling reliable polymer identification directly in water matrix. Beyond qualitative identification, SARS can also be applied for quantitative analysis of microplastics. It is typically achieved by constructing calibration curve, where the intensity of a selected characteristic SARS peak is plotted against known concentration of microplastic. Many studies report good linear relationships over environmentally relevant concentration range. To improve measurement reliability, internal standards such as silicon thickness and reference dyes are often used. These standards help correct for signal fluctuations caused by variation in laser intensity, substrate uniformity, or sample positioning. More recently, machine learning techniques such as convolutional neural network, principal component analysis, and support vector machine have been introduced. These methods allow automatic classification of polymer types, separation of overlapping spectral features, and improve identification accuracy in mixed microplastic samples. By combining enhanced SARS spectra with calibrating strategies and intelligent data processes, researchers can achieve both accurate identification and reproducible quantification of microplastic in complex bottled water samples. In terms of analytical performance, SARS demonstrates excellent sensitivity, accuracy, precision, and selectivity. The sensitivity is particularly impressive, with report detection limit approximately 15 nanometers, which is by far superior to conventional FTIR and standard Raman microscopy. Regarding accuracy, recovery value typically range between 92 and 105%, which indicate minimal systematic error. With high precision, with relative standard deviation generally below 10%, demonstrating good repeatability. In addition, SARS exhibits strong selectivity as it can distinguish multiple polymer types in mixed sample due to unique fingerprint nature of Raman spectra. Despite its strong performance, SARS has both clear advantages and notable limitations. The key advantages include the ability to detect both microplastic and nanoplastic, rapid analysis within minutes, minimal sample preparation, and non-destructive measurement directly in water. However, several challenges remain the same. One major issue is substrate variability, which can affect reproducibility. There may also be metal interference from salt and organic matter in real water samples. Additionally, high quality SARS substrate can be costly, and spectral interpretation often requires technical expertise. To address this challenge, future improvement may include the development of mass-produced and standardized substrates, integration with artificial intelligence and machine learning, and the creation of portable or smartphone-based SARS system. Hybrid approach combining SARS with filtration or microfluids may further enhance real-world applicability. So from the article, me and Aiman can conclude that SARS enables rapid, sensitive, and selective detection of microplastic in bottled water. It successfully overcome many limitations of FTIR and conventional Raman technique, particularly for nanoplastic, which are otherwise difficult to detect. So, recent study published between 2020 and 2023 demonstrate that SARS, especially when combined with advanced data processing, has strong potential as a routine environmental monitoring tool. Therefore, SARS represents a promising pathway toward accurate and real-time monitoring of microplastic in drinking water. So, we have reached to our end presentation. That's all for me and Aiman. Thank you. So that's all for me. Thank you.